Okay, as we previously discussed, the power series method doesn't work for every problem. It doesn't work for problems where you have negative exponents. It doesn't work for problems where you have fractional exponents. But sometimes there are a couple of notable exceptions. So in this case, we're going to look at an exception where we're going to solve an ordinary differential equation of the following form. So first of all, I want you to notice you can't directly solve this using the power series methods because your functions are not analytic at x equals 0. Now, what does analytic mean? Analytic means if you were to write a power series for b of x over b of x, that it wouldn't necessarily converge around 0 because as x goes to 0, the 1 over x term goes to infinity, and as x goes to 0, the 1 over x squared and x over x squared go to infinity. So it doesn't necessarily converge around the point x equals 0. So you couldn't just sit down and use a power series method because it violates the rule and may not have a non-zero radius of convergence. So the approach here is as long as A and B are themselves analytic, so let's go back and see what A and B were. So B is the function here, and I'm sorry, that's B and C. That should be B and C. B is the function here, and C is the function here. So as long as these two functions are analytic, we're going to say that there is a solution. And the only modification is, instead of the normal power series solution, we're going to multiply that by this x to the r, where r is some index that we'll determine later. So here's our x to the r, and here's our series expansion. And so we don't yet know what r is. So we're going to rewrite this equation on the next page. So here's our differential equation. We've multiplied everybody by x squared. We're going to assume that B and C can be written as power series. So here's their power series equivalent. And we're going to assume that there is this, this solution r times mx to the m summed over m equals 0 to infinity. So we have this x to the r out in front. So when we, in fact, let's go back and just look at that solution form again. It's in here somewhere. Here we go. So we've got this x to the r, mx to the m. So we're assuming this is a solution. We're going to substitute this for y of x. So remember, the other thing we need to substitute is y prime of x and y double prime of x. So we take that and we take its derivative. We've taken that x to the r into the sum and made this m plus r, and then when you take its derivative once, m plus r comes down and your exponent is m plus r minus 1. And so if you do that and just look at a little expansion term by term, it looks something like this. The second derivative of y, do the same thing. We're just going to take the derivative of this equation and end up with this one. So now we have expansions for y, b, c, y prime, and y double prime. So we put everything back into the equation. And so what we get is our first term does not have a b and a c, and it does correspond to the m equals 0 term. So it is the lowest order term, this first term is. And then our second term contains the b of x, and our third term contains the c of x. So we have those expansions. We still have our x to the r. We now have our expansion for y prime and our expansion for y double prime. So we've substituted everything, and now what we want to do is we want to equate equal coefficients of x, or coefficients of equal powers of x. And what we find is for the lowest order term, okay, and that would be, in each expression, that would be the x to the r term. So the first term, we have this r times r minus 1 times a sub 0. The second term, x to the r, the lowest order term, would be b0r. And the third term, it would be c sub 0 right here, times x to the r. So we're collecting these coefficients multiplying x to the r. In this term, we pick up an a sub 0, we pick up an a sub 0 here. So if we collect all those terms for the power x to the r, this is the equation that we get. And this is going to be an important equation because it's known as the Ingersoll equation. And the reason it's important is it allows us to solve for r. Okay, so the next step is to find the roots of this equation, and then depending on what the roots are, we get three possible cases. So remember A naught, B naught, C naught. These are all expansions. So in case one, we're going to have some roots that don't differ by an integer. So we'll have an r1 and an r2. And if that's the case, then we have a solution y1 that is x to the r1 times the series, and we have a solution y2 that's x to the r2 times the series. So the r1 and r2 would just be two distinct numbers, not differing by an integer. In case 2, the roots are equal, and so we have a double root situation. And so our first basis solution is just an x to the r times a series. Our second base solution is an x to the r times a series with different coefficients. But we add this y1, which is our first solution, times the natural log of x. So this is very similar to the case where we had repeated roots when we had a solution of the form e to the lambda x. And when we had multiple roots, we had to take our solution and multiply it by x. Here we're multiplying our solution by the natural log of x to obtain a second linearly independent solution. And the reason this is the natural log is that we're dealing with solutions in x to the r, not e to the lambda x or e to the gamma x. So because we don't have the exponential function, this natural log shows up in the solution. So this is our case 2 where we have multiple equal roots. In case 3, the roots differ by an integer, and this just gives us, if we assume r1 is the larger root, then that gives us this standard series expansion multiplied by x to the r1. Then we have that solution plus a second solution where we have r2, but then we have the natural log of x and some constant k. So this is the case where they would differ by an integer, case 3. So that's the method of Frobenius. It's used primarily to solve Bessel's equation. So in the next lecture, we will very briefly show Bessel's equation and what the solutions look like, because Bessel's equation also is an equation that's pretty important in engineering.